that if the sampling rate is less, very, very small, then there is a problem of reconstruction of the original signal from the sampled version. However, it is possible to reconstruct the analog signal from its sampled version if and only if certain criteria is fulfilled. The criteria is called Nyquist criteria. And I told you that the Nyquist criteria is Fs greater than equal to twice W. This is the Nyquist criteria which should be satisfied for faithful reconstruction of the original signal from its uh, uh, sampled version. Okay, now this twice W here, W is the bandwidth of the input signal. Input signal means it is the bandwidth of the actually analog signal, analog input signal. And Fs is the sampling frequency. Yes?
So which slide are you presenting, sir, right now?
I am not presenting anything, any slide now. Just I am discussing what I have discussed earlier. Okay. Just for recapitulation, then I will start sampling and hold circuit, discussion on this sampling and hold circuit. So I am discussing actually the previous thing, this means this Nyquist criteria, okay, and aliasing effect. Just to recapitulate the previous part, because I will tell you a special kind of filter is used before sampling and hold circuit. That filter is called anti-aliasing filter. So if some students actually, for example, was absent in that class, so he will not understand, he or she will not understand what is anti-aliasing filter and what is the necessity of using anti-aliasing filter. What is aliasing? He or she does not know at all, but anti-aliasing is coming here. Anyway, so that's why I want to recapitulate the previous part of the signal of this class. So the Nyquist criteria, F is greater than equal to twice W, that is actually the criteria which should be satisfied for faithful reconstruction of the analog signal from its discrete counterpart. Here, W is the bandwidth of the analog signal or continuous time signal, and Fs is the sampling frequency. Reciprocal of Fs, where I can write Fs is equal to 1 by Ts. Okay. So Ts is called actually sampling frequency. So you can write this Fs is equal to 1 by Ts. So here I want to write to suppose this is our analog signal and the bandwidth of this analog signal, this is our analog signal, bandwidth, analog signal xt. Okay, and bandwidth xf is the frequency domain of this xt, which can be obtained by taking Fourier transform of xt. And from the description of xf, you will get the bandwidth of the signal. So let us consider W is the bandwidth, W hertz is the bandwidth of the signal. And I am thinking that this signal is band limited. Band limited means it has finite support, finite bandwidth. The number of frequency components are considered finite. Okay. So the bandwidth is W. Now, if this signal is sampled like this, for example, this is one sample, this is another sample, this is another sample, you will not take any value in between two successive samples, and only these sample values you are taking. So suppose these are the sample values for this signal. After sampling, you will get these sample values. Clear? These are the sample values. Okay. Now, here the signal is uniformly sampled. Uniformly sampled means if you take any two successive samples, then the distance between two successive samples is suppose Ts, and this horizontal axis is representing T, and this vertical axis is representing the amplitude of the signal xt. Here, the signal frequency fs is equal to 1 by Ts. Ts is the time period, sampling time period. Ts is sampling time period. Sometimes it is simply called sampling period. And Fs is called sampling frequency, which is reciprocal of Ts, sampling frequency. And Nyquist theorem, Shannon-Nyquist theorem tells that if this Fs and sampling frequency is greater than equal to twice W, then it is possible to reconstruct this analog signal from these sample values. For example, your sample values will be given. Suppose in your hand only these sample values are there. Let me draw here another signal to understand this. Suppose you have the sample values like this. The sample values like this. You have the discrete sample values. Okay, but you don't have any value in between these two successive samples. But what you want to find out, you want to find out the analog approximation of this signal from which this sample sequence has been obtained. From which continuous time signal you have obtained this signal, that continuous time signal, continuous time analog signal is to be determined from the given samples. So in your hand, these samples are there, and you want to find out a signal like this. For example, just I am connecting smoothly the peaks of the samples, and this is called sometimes envelope or interpolated signal. So this signal, this continuous time signal, you have to estimate, you have to find out, or you have to determine from the given sample values. Given sample values means these sample values, these samples are given to you, and you have to estimate this black signal. Okay, let us consider this signal samples are given by xpt as a sample signal, or sometimes it is written by xst also, whatever you can do. In your PPT, most probably it is given xst. This xst is the sample signal, and this signal is the analog signal xt. Okay, so here xxt will be given to you, and means this sample values will be given to you, and you have to determine this xm reverse process. From the sending end, when you are storing the signal data in your computer, what you are doing, you are suppose one song you have to store in your memory, in your storing device, for example your pen drive. So it will be stored in pen drive in the form of in digital format. Okay, now if you want to store this, then what you can do, you can sing a song in front of a microphone, and the microphone, this will generate some electrical signal at the output. Microphone will catch the sound signal, and it will be converted to electrical signal through a transducer. This transducer is called microphone. It is actually converting one kind of energy to other kind of energy. The sound energy is converted to electrical energy. So the microphone output will be the electrical image of the sound signal. So this microphone output, which is electrical signal, that is a continuous time signal. Okay, continuous time signal, and if you want to store that song in your digital device, then obviously you have to pass this signal through a number of stages to make it, to convert it into digital format. So initial stage is that you have to filter that signal. If some noise may be there, some noise may be there in the output of the output of the microphone, then you have to filter that. Then you have to actually you have to um, magnify the signal by using some amplifier. You have to amplify the signal by using some amplifier. Then after amplifying the signal, if you see some other noises are there, then you have to filter that noise by using a filter. And at the same time, what I want to say, that the signal cannot be time limited at all. Actually, a signal, sorry, frequency limited at all. I told you that frequency limited means band limited, I want to say. If a signal is time limited, it cannot be band limited. But when I am talking or I am singing a song, then that signal is time limited. For a fixed time, you are singing a song and then it will be converted into the digital format. That means for certain time, the signal is present, and outside this time, the signal is not present. Therefore, that continuous time signal is time limited signal. It is not time. It is not spread up to infinite time. It is time limited signal. It may be that the song is of 5 minutes. It may be that the song is of 3 minutes, something like that. That means the sound wave or sound signal is limited in time. And our Fourier transformation theory tells that if a signal is time limited, means it is limited in time, it cannot be band limited. Okay, so a time limited signal has infinite number of frequency components in the frequency domain. For example, I am giving this example, then your concept will be clear. Then I will discuss about this part. Suppose I have a signal like this, and signal is limited up to this. Suppose it is 0 time. That means I am starting the song at this moment, and suppose this is 3 minutes or 5 minutes. Let us consider this is 5 minutes. So this is a this signal. What I am showing here, a blue curve. Okay, this signal is time limited signal because the signal is defined. The signal value is defined for a limited, means a certain interval, for a certain interval of time that is finite, 0 to 5 minutes. Beyond this 5 minutes, there is no signal. Therefore, it is called time limited signal. And our Fourier transformation theory tells that if the signal is time limited, then it cannot be band limited. So it will be in frequency domain. If this, suppose this is your xt, it is time domain signal. Okay, and in frequency domain, the signal, a horizontal axis is your frequency, and the signal will be like this. The signal bandwidth will be extended up to infinite. If the signal bandwidth or signal frequency is extended up to infinite, then what is the problem? Problem is that this is not band limited. Why a time limited signal cannot be band limited? This is due to the fact of reciprocity between time and frequency, because you know time and frequency, they are reciprocal to each other. Dimension of time is second, and dimension of frequency is 1 by second or hertz. Okay, so 1 by second means actually it is the reciprocal to this this time. So that's why actually from this concept it is clear that Ts is equal to 1 by Fs is equal to 1 by Ts. Therefore, time and frequency, they have inverse relationship. So if a signal is time limited, then it cannot be band limited or frequency limited in frequency domain. Again, if a signal is frequency limited in frequency domain, then it cannot be time limited in time domain. But whenever I am capturing the signal, I am capturing in time domain, for example, and I am seeing that the signal is limited in time. the signal is actually described for a certain interval of time. And therefore, if I convert that particular signal into a frequency domain signal by transforming this signal into the Fourier, transforming this signal by using a Fourier transform technique, then I will see that the frequency components are extended up to infinite and it is not band limited. However, the beauty is that it will be visible to us. If you find out the Fourier transformation of the signal, then you will see up to a certain amount of frequency, the magnitude is higher. Magnitude of the frequency components will be higher. And beyond that frequency component, beyond that frequency value, for example, this is the cutoff frequency, and beyond this cutoff frequency, the values of the frequency component will be abruptly small, will be so small that we can reject those frequency components. And here, if this is the origin, you will see that it is the frequency band will be mirror image. It means right hand side of the frequency image will be mirror image of the left hand side, or left hand side of the frequency domain will be mirror image of the right hand side. Okay. Okay. So the frequency value at this point will be equal to, for example, frequency point at the, so this is actually symmetric on both sides with respect to the vertical axis. It will be same, and it can be proved also if you take the Fourier transform. If you see the properties of Fourier transform, you can get it. Okay. And what I want to say that if I consider a frequency, for example, this is the cutoff frequency up to which the frequency values are means significant, and beyond that the frequency values are not significant at all. And let us consider within this band, here it is, if I think that this is 0, so this part will be negative. So this negative frequency components will not be physically realizable by using instrument. But what I can do, I can say that the bandwidth is FC. Now here, in place of FC, I will write W, because I have told that my signal is band limited in W. That means this cutoff frequency FC is W here in my case. And I am thinking that beyond this W, the frequency values are so small that we can neglect those frequency component. And if you neglect that frequency component, and if you pass only this part of the frequency, if you consider only this part of frequency, and again if you take inverse Fourier transform of this, the time domain signal will be approximately equal. It will take approximately this shape, but obviously it will not be sharp edge. There will not be sharp edge here. Edge will be something like this, and the time will be extended like this. But after a certain interval of time, the value of time will be so small that I can neglect that also. Therefore, I can say that this time domain signal will also take the same form as previous. Okay. So here, these frequency components are negligibly small. So this is the bandwidth of the signal, and I will say that this is a band limited signal. These frequency components will be rejected by using a filter, and I will design some filter which is called anti-aliasing filter. Anti-aliasing filter. It is nothing but a low pass filter. Low pass filter means it will pass only a band of W frequencies. Up to W, it will pass at the output, and beyond W, these higher frequency components, beyond W, this higher frequency component will not be passed. Therefore, I will say that this is a low pass filter. So anti-aliasing filter. And why I need this filter? This is nothing but a low pass filter, I told you. Okay. And why I need this filter, I will say that now at this moment. Okay. Since the signal is not time limited, therefore the bandwidth of the signal is ideally infinite, because infinite number of frequency components are there. Since the signal is time limited, the frequency components are extended up to infinite. So ideal bandwidth is infinite. But if the bandwidth is infinite, so W tends to infinite in that case, then what should be Fs? It should be infinite. So Fs means infinite, means actually Ts is equal to 0. Then at every instant you have to take the samples. No, it is not possible. Then number of sample will be infinite. Okay, clear? So in that case, number of sample will be infinite. So I should get some value W which is finite. And how can I make it finite? By using a low pass filter. I will take some low pass filter having bandwidth W, and at the input of the low pass filter I will send this signal, and the signal will pass only this amount of frequency, only this much of frequency components, rejecting the other part of the frequency component. So other part means these frequency components will be rejected. Now, if you take this part of the signal only, now you are getting a signal of finite bandwidth W, and it is done by a filter which is a low pass filter. Okay, and you know our signal frequency, the sampling frequency should be greater than equal to twice W for faithful reconstruction, where Fs is equal to twice W is called the Nyquist rate, and Fs greater than or equal to twice W, it is called Nyquist criterion, Nyquist, Nyquist criterion. Okay, now I can satisfy this inequality if and only if W is finite, and this, since this low pass filter is actually making this bandwidth of the signal finite without making much distortion of the signal in time domain. Therefore, this is called anti-aliasing filter. Unless you satisfy this condition, then it is not possible to satisfy this particular Nyquist criteria. And if you cannot satisfy this Nyquist criteria, then obviously aliasing effect occurs, because I told you that if it is less than twice W, then aliasing effect occurs always. If W is equal to infinite, then it is not possible to take you to make this Fs infinite, because Ts cannot be 0. Sampling interval means actually sampling period means it is the distance between two successive samples. It cannot be made 0. So Ts is always finite. That means Fs is always finite. So if W is infinite, then Fs is finite. That means Fs less than twice W, then aliasing occurs. So to avoid the aliasing effect, you have to make this W finite by using some filter, which is a low pass filter. This filter has one name, that is called anti-aliasing filter. And this anti-aliasing filter should have a bandwidth W also.
So you're not audible, sir.
How long I am not audible?
Sir, a few seconds, sir.
Few seconds. Okay. Okay. So now, what I want to do here, if I want to sample, if I want to sample an analog signal, then first of all I will send the analog signal through an anti-aliasing filter. This is your anti-aliasing filter. Then I will use some sample and hold circuit. This is your sample and hold circuit, and it is written this form, sample and hold circuit. This sample and hold circuit will sample the signal, and anti-aliasing filter will fix up. This is low pass filter with bandwidth W. Bandwidth is equal to W. And at the input you are giving this signal xt, and here at the output you are getting some sample signal xt. Okay, so the function of the anti-aliasing filter is just to make the signal xt finite bandwidth signal. It will make it finite bandwidth signal. So that I can fix up a rate fs, or I can fix up a time period, sampling time period ts, so that I can satisfy the Nyquist criteria fs greater than or equal to twice w. Is if w is defined by this anti-aliasing filter, then I can fix up this fs value, and then after fixing up this fs value, I can maintain this Nyquist criteria. Since I know what is the bandwidth of the anti-aliasing filter, then obviously it is possible to avoid the aliasing effect. Okay, so this is the requirement of anti-aliasing filter before the sample and hold circuit. Now I want to discuss about the sample and hold circuit. What is the structure of sample and hold circuit, and how can I?
So one question in the previous
Uh,
diagram. In previous diagram, could you go back to that?
this diagram?
Yes, sir. Yes, sir. Sir,
Yeah,
X is the sampled signal, right?
sample this output xpt is the sample signal. Xpt output of this sample and hold circuit. At this point, this is the sample signal.
So in the slides XST, right?
Oh, okay. In slice, if it is given excelsior, so you can write. Okay. Anyway, yes,
Yes. Thank you.
you can write here x guest. Okay. This is sample signal. Okay. If I make any mistake in nomenclature, then please you inform us. This is good point. Okay. So this is our the sample signal. Clear? Now next I want to discuss this block. What is there inside the block? What is the rudimentary circuit diagram? Here you see the circuit diagram of sample and hold circuit is quite complex, not heavy complex, but quite complex, because here sometimes some MOSFETs are used, sometimes with MOSFETs some operational amplifiers are used for getting better performance. Okay, but here I will draw a rudimentary circuit diagram, means as simple as possible. I will write that to just to understand how the sampling and hold is performed. Okay. Now, for this, let us see. Actually, I have shown as diagram like this. This is a block diagram form. Okay. At the inside, you are giving some voltage signal. Okay. V in, and at the output you are getting the output voltage, that is sample voltage. So in block diagram I have written here in the form of voltage. Okay, no problem. It may be current, it may be other things also. But since I am thinking about electrical circuit, then it will be either voltage or it will be either current. Okay, it will be either voltage or current. Now this is sample and circuit. Sample and circuit means, actually sample and hold circuit means uh, the circuit will sample at every ts time interval, and it will hold after sampling at a particular time instant. It will hold the value, or it will hold the voltage or the value of the signal for a certain duration, and this duration can be controlled by another timing circuit or another clock applied to the sample and hold circuit. And in sample and hold circuit, actually either I may do like this. Just let me show here. This is this continuous time signal here, xt, and xkt is a sample value at ts time instant, a kts time instant, k is the integer and ts is the sampling interval. Okay, so the value at this point will be xkts. Clear? And here this xkts, this is also for, suppose for k is equal to 1, this is for k is equal to 2, this is for k is equal to 3, so and so on. So XKTS, the collection of XKTS will give you the XST. XST means actually the sample signal. But here we are calling this circuit as sample and hold circuit because suppose for this particular instant, sorry. At this particular instant, the signal is sampled. Okay, then it is holding the circuit is holding the voltage up to certain time interval. Then it may be discharged like this at this point, or it can continue to hold up to this next sample. It can do anything based on the operation of your circuit or based on the clock applied to your circuit. Either it will hold up to a certain time interval for like this. This is the time interval. For example, tau is the time interval. So the voltage is held by the circuit for a time tau. Then it will be discharged. Then again, it will sample in this time instant, and again it is holding the voltage, and it is getting discharged again after tau time. Then from tau time to again here, it is sampled here at this point. Then it will hold the same value for a certain time period tau. This is also tau actually. This is also tau. This is also tau. Okay. Then again, it will discharge. Then it will wait for the next time interval, starting time interval. Okay. So in this way it can continue, or it can continue in other way also. This tau may be extended up to the next pulse, next sampling time instant. This is the first time instant. Suppose this is the first time instant. This is the second time instant. So here what we are doing, the signal is sampled at this time instant, and then it will hold the signal or voltage up to this time, up to the next, up to this time interval, until the next sample is coming. So then again it will be charged, or the signal will take this sample value at this point, and again it will continue to stay up to this time, and then it will come to this, and then it will come to this like this. You can do this also. In different books, different patterns are there. It depends on the pulses, clock pulses we are applying at the input of the sample and hold circuit. Now let us see what is the basic diagram of sample and hold circuit. This is the basic diagram, means rudimentary diagram. Okay, so some associated circuit can be installed here based on operational amplifiers to improve the performance. However, if you take this, then it is possible to describe how sampling is performed actually by using the hardware, electronic hardware. Now, can you identify this particular device? What is this device? What is this device? Anyone? It is one field effect transistor, FET. It is FET. Okay, junction FET. It is FET, means several types of FETs are there. You know, JFET, MOSFET, CMOS, etc. and etc. PMOS, NMOS. Different types of field effect transistors are there. This is JFET, and JFET junction field effect transistors are also of two types. One is called N-channel JFET, another is called P-channel JFET. So one is called N-channel JFET, and another is called P-channel JFET. Here, the symbol says that since the arrow sign is given like this in the gate, how many terminals are there for JPET? 3 terminals. One terminal is called source, another terminal is called gate, another terminal is called drain. So three terminals are there. Can you remember this? I think you have studied this part in analog circuits class. Can anyone remember?
Yes, sir.
Okay. So this is actually this FET, JFET, this is actually N-channel FET. Okay. This is your N-channel FET. In case of P-channel FET, the arrow sign will be in this direction, an opposite direction. Okay, in the gate. Actually, the arrow sign is put in on the gate to understand that what type of JFET is this, whether it is N-channel JFET or it is P-channel JFET. For N-channel JFET, arrow sign will be towards this, and for P-channel it will be away from this. Okay, this is one JFET. Now, how this JFET, this first JFET is acting as sampling switch, and the second JFET is acting as discharge switch. Okay, sampling switch and discharge switch. How a FET can act as a switch? Do you have any idea on this? Can you remember the structure of JFET, internal structure of JFET? Otherwise, it will not be clear. You can, yeah. What is that? How can a JFET can be constructed? A JFET is something like this. I am drawing here. A JFET is nothing but a silicon bar like this, having heavy doping in both sides. This and this, heavily doped. These two sides are heavily doped. If this substrate, this rod, okay, if this is N-type substrate, then you have to dope P plus. You have to make this region P plus region, this region P plus. That means it is heavily doped by holes. Heavily doped by holes means so many holes are there. This part also P plus doping. Okay, and these two, from these two sides, two leads actually will be connected.
Sir, whiteboard not visible.
Whiteboard is not visible.
Yes, sir.
Why? Just I am sharing once again. Now is it visible?
Yes, sir, visible.
Then these two sides will be connected to each other like this by using a conductor wire, and that is actually gate G, gate of the JFET. And since here this is N-type substrate, therefore this is called this gap between these two heavily doped region is called the channel. And this channel is N-type channel because these are P plus type. I have taken N-type substrate, silicon substrate. Therefore, this region is actually N-type region, and these two regions are actually P-type regions. And in between these P plus type regions, one channel is there. This is the channel. And one side is actually, suppose this side is source and this side is drain. And here from one side to other side, the electron will flow. For example, from source to drain, the electron will flow in this direction and the current will flow in this direction. And the amount of current will be dependent on what? Gate to source voltage. Generally, gate to source voltage is kept negative. That means gate to source junction means gate to source junction is kept here like this. Suppose this is gate and this is your gate, and suppose this is source. This gate is kept negative with respect to the source and with respect to the drain also. So this negative voltage actually makes this junction reverse bias. This and this junction reverse bias. If these two junctions are reverse bias, then automatically the depletion region will increase. Where there is NP junction, there is a depletion region. And depletion region means it is devoid of mobile charges. Some ions are there only. So when you are making more and more negative, the gate is made more and more negative with respect to the source and drain, then automatically this region, this depletion region increasing and the channel width is decreasing. Therefore, lesser and lesser amount of electrons will propagate from source to drain. And if you make this gate signal, this gate voltage such that these two regions, these two depletion region touches to each other, then the channel will be blocked and pinch off occurs. At this time, the voltage, gate to source voltage for which this occurs, that means these two depletion regions touch to each other, then no electron will flow from source to drain, and it will act as open circuit device, switch open condition or open switch condition. It will not pass any current from input side to output side, means source to drain. It will not permit any current conduction of electrons from source to drain, and consequently there will be no current from drain to source. So this is pinch-up condition. So at pinch-up condition, there will be no. So pinch-up voltage is that negative voltage which is applied to the gate for which the FET will be switched off. There is no current, open circuit, switched off. And when the voltage is, for example, 0 or slightly positive, then there is a big channel to pass the electrons from source to drain, and I will say that this FET is in open condition. It's closed switch condition, or large amount of current will flow. This is switching condition. Therefore, based on this gate voltage, I can control the switching operation. When the FET will be switched on and when the FET will not be switched on, it will be switched off, that will be determined by this gate signal. So what's the time now? Okay, today I am leaving. So next day I will discuss this part to make this operation clear. Okay. Okay.
Sure.
Yes.
So could you upload the slides, sir?
Upgradation to partial. I have done this partially, so it is not completed. I can give it in this week. Okay. At the in the next week, I can give it in the next week on either on Thursday or on Friday. Then I am not taking any class, so you will get enough time to study this part. Okay.
Sure.
And at the same time, you are also copying this, means you are recording this voice, so you will get it from there also, no problem. Okay. Okay, let me